Hello, students. We're going to do some linear algebra in this class, and you guys have seen matrices, hopefully, and you know that matrices have things inside them. Well, what kinds of things? You might say, well, numbers, but what kind of numbers are we allowing in our matrices? For example, we might run into trouble if we had a matrix like this one here, 2, 3, 5, 6, and we wanted to row reduce, and we were only working inside the positive integers, right? Or even in just the integers. The first thing I might want to do is I might want to subtract or add a negative multiple of the first row to the second. But what would I want? Well, I'd want to subtract off 5 halves of the first row or add negative 5 halves of the first row to the second, so that this 5 will disappear in the next step of row reduction. If I'm only in the world of whole numbers, 5 halves doesn't exist. So I want to be careful about what number systems I'm going to be using when I do this sort of thing. So let's discuss that first. And what we're going to do in this class is we're going to stick to something called a field. Now there are many, many different fields, so we're not going to do every field, but many of the results we're going to be proving, well, they work regardless of what the field is. So we're going to just assume that we have matrices over a field. I have to tell you what a field is, though. So we definitely want addition, right, and multiplication, right? But we also want to be able to take multiplicative inverses, right? Because we want to be able to take things like 2 times 1/5. So that would be a multiplicative inverse. So what is a field? A field is going to be a set of some numbers that we're going to be using that has 2 operations, times and plus. And if I call my field f, I'd say these both take in 2 elements. So we could see it as a map from the Cartesian product of f cross with f to f. So multiplication takes in 2 elements, spits out an element of the field. Addition takes in 2 elements of the field, spits out an element of the field. And we want some rules. We don't want just multiplication to be anything. So we have 5 rules for our field. Here's what we'd like. We'd like commutativity. And this is of both times and plus. That just means AB equals BA, A plus B equals B plus A. So it means you can switch the position of the two. We want associativity. Of both. And that means A times BC is equal to AB times C. So this means you can move parentheses. Notice that with this rule, we're not moving the position. A is still first, B is second, C is third. If I want to move position, I need commutativity. Associativity is when we want to move the parentheses, decide which takes place first, but the order stays the same. And the same is true for addition as well. We could do this, but I'll leave that. You get the idea. It's the same thing with pluses. What else do we want? Well, we want identities for both. So, for example, 1 as a standard is the standard name of, not always, but the multiplicative identity, something where if you multiply it by 1, you get the element back, whatever that element is, or 0 for our additive identity. And like I said before, we could use different names for these things, but we have to have something that acts in that fashion, right? So being an identity, like let's say I wanted to call my identity E, like we often do in group theory, we would need something where EX equals XE equals X. So something that sends things to itself, like 1. When you multiply 1, whatever you multiply it to, you get back the same thing. 0. Same thing with addition. If you add 0, you get back the same thing. And it doesn't matter which side as well. Now, inverses is the first thing where it's a little different. We want inverses. We want inverses for anything additively. So that means we could always get back to 0. For example, if we had an element 3, we would want some element that takes us back to 0 when we add it, like -3. With multiplication, we don't demand inverses of everything. There's one special number that we don't ever want to take the inverse of in algebra and pre-calc and all of that, and that's 0. We don't want to take 1 over 0. We don't want to try to create a system where that's allowed because a lot of other things break down. So we want the inverses of everything except for 0 here, and the inverses of everything with respect to addition. So whatever number it is, we have to have an additive inverse, something that we can add and it will take us to 0, and a multiplicative inverse, something where if we multiply it, it takes us to the multiplicative identity, which is 1, except for 0. And then finally, we have a distributive rule. And notice, this is the one that's connecting times and plus. Whatever our times and plus are, whatever our collection is, this is what's connecting those two together. And it simply says that A times B plus C is equal to AB plus AC. That's what it says. We do not have a rule for this, but you probably wouldn't be expecting a rule for that unless you worked in very particular places. But this is our distributive law. It connects multiplication to addition. And these are the 5 rules that we want out of our field. So a field is just a set with 2 operations that keep us inside the set. They're closed. They don't send us somewhere else. Otherwise, we wouldn't be a very good system if we had to look at a new system every time we tried to add or multiply. And it satisfies these rules. Now, what are some very simple things which are fields? Well, what isn't a field? Well, the naturals are definitely not a field. The naturals meaning 1, 2, 3, and so on. I mean, we don't have additive inverses here, right? If I have 3 and I want to get to 0, there's nothing that I can add to 3 that would take me to 0. As a matter of fact, I don't have an additive identity of 0 here because 0 is not in the natural numbers. So I lose out on identity. I don't have multiplicative inverses. This, because there's no 1/3, is a difficult place to do the kinds of things we want to do. So we're not going to be considering that. Also, not a field. So not, don't think that it's a field because I've been talking about fields. Not, no, don't try and use this in this class inside our matrices. The integers, also, no, doesn't work out. Here we have additive inverses and we have an additive identity. We have a multiplicative identity, but we definitely do not have multiplicative inverses here. We do have associativity and commutativity in these, but what other places do we have? Well, we have the rationals, or the quotients, right? And this is the set of all P over Q, so that P and Q are integers. And of course, we require one more thing, and Q is not 0. So basically fractions. And if we start with fractions, this is closed. I can add and multiply all I want. I'm going to stay inside the fractions. And I'm not going to accidentally slip out. And then finally, the mysterious reals, which are actually, I mean, they're where pre-calc and calc takes place, but they're much more complicated and more difficult to define, but they include all the numbers, the square roots, the e's, and the pi's that you're used to. So it's the hardest of of any of these 4 systems, but it's the one you're most familiar with. And this is quite often where we'll be working. But I want to introduce another system where we might want to work as well in this next video.